All right, everybody, welcome. This video, we're going to basically want to just go over several limit calculations, um, just to kind of give you some examples in case you get stuck. Okay, so I'm just going to jump right in here. So here we go. Let's say we have this problem: limit as x approaches 4 of x squared plus 5x plus 4 over x squared plus 3x minus 4. Okay. Now, I will tell you that most limit problems of this sort have to be factored, and then you cancel something, and then you can find the value. But you want to make sure, though, that you make sure that you can't directly substitute. Okay, so the idea is, polynomials are continuous. Okay, so x squared plus 5x plus 4 is continuous. X squared plus 3x minus 4 is also continuous. Now, the only place where we have to worry is where the bottom is 0, because that gives us division by 0. And before we first want to see if that's a problem. So if I plug in 4, I get 4 squared plus 5 times 4 plus 4 over 4 squared plus 3 times 4 minus 4. Okay, and 4 times 4 is 16. 16 plus 4 is 20. We get 20 plus 20 because 5 times 4 is 20 as well. And then let's see, we get 16 plus 12 minus 4. And there we go, 40 over, and then 16 plus 12 is 18. 18 minus 4 is 14. So 40 over 14, of course, it's going to reduce to 20 over 7. And there we go. So this happened to be a problem where we didn't have to cancel anything. We didn't have to factor. We could just plug it in, which is the easiest type of limit problem, where you can just plug the thing in. Again, the reason that we're able to do that instead of having to do a left and right hand limit is because both of these functions, top and bottom, both of these functions are continuous at x equal 4. Not only that, but also the bottom is not 0 at x equal 4. If the bottom were 0, then we would have the function would be undefined there, and we would have an infinite discontinuity. Okay, let's consider this problem. Okay, so there's number 1. So I'll change my color here. Problem number 2. Let's say, okay, it's going to be the same function, but instead of positive 4, let's consider negative 4. And maybe this time you might see what's coming. So same function. Okay, now if I attempt to plug in x equal negative 4, let's see what happens. We get negative 4 squared plus 5 times negative 4 plus 4. Yeah. Over, and then we get negative 4 squared plus 3 times negative 4 minus 4. And let's see what happens here. Negative 4 squared is 16. 5 times negative 4 is going to be negative 20. 16 minus 20 is negative 4. Okay, so in other words, look, this is 16. This is negative 20. 16 plus negative 20, if we add those together, we get negative 4. Negative 4 plus 4 is 0 on top. And now on the bottom, we have positive 16 here, minus 12. 16 minus 12 is 4. 4 minus 4 is 0. Okay, so here we go. We have a 0 on the top and a 0 on the bottom. Okay, anytime this happens, you might be inclined to say this is undefined, and in a way it certainly is. But we have a special name for this. This is called an indeterminate form. And the reason it's called indeterminate is because there's things that we can do to these functions to get more information about what's actually happening with this limit. So in other words, we don't know what the answer is. Is it 0? Is it undefined? We don't know. Is it some other number? Again, we don't know. So this is when we have to start factoring. Okay? So, yeah, we have to factor now. That's what separates this problem from the previous, and most problems of this type are like this. So let's go ahead and factor the top and bottom. So limit as x approaches -4. And let's factor the top, right? So two numbers that multiply to +4 that add to +5. That's going to be 4 and 1. X plus 4, x plus 1, over, and then two numbers that multiply to -4 but add to +3. How about +4 minus 1? And now look what happens, right? The x plus 4 cancels, because x plus 4 over itself is 1. We get limit x approaches -4 of what's left. Okay, now I want to point out that this function is exactly the same as this one. Okay, so I'm going to emphasize this. I'm going to change my color again. These two are exactly the same. Okay, with one exception. Okay, except at x equals -4. Okay, exactly the same except at x equals -4. Our original function was indeterminate at x equals 4, but our new function, which again is different, is perfectly defined at x equals 4. X equals -4. So if I plug in -4 now, I get -4 plus 1 over -4 minus 4. -4 plus 1, -3. -4 minus 4, -8. Negative over negative is a positive. We get 3 over 8. Okay? And so, 3 over 8 is certainly different than 0 over 0. So this is what an indeterminate form is all about. You get a 0 over 0, and it didn't turn out to be 0. It didn't turn out to be undefined. It turned out to be 3 over 8. So that's why we call it indeterminate, because we have no idea what it is until we do something else. In this case, we had to factor and cancel. Good. So there's that problem. So if you see two polynomials being divided and you get something like this, now we know what to do. We can factor. Something's going to cancel. Then plug it in. Good to go. Okay. Let's see. Let's do some more, right? Let's see. So we'll start with green. Limit as x approaches -1 of x squared minus 4x over. So this one's very similar. I'm doing another one just so you see how similar these actually are. Okay. If I attempt to plug in -1, -1 squared minus 4 times -1 over -1 squared minus 3 times -1 minus 4. If I do that, -1 squared is 1. Negative times a negative is a plus. Over. Let's see, -1 squared, 1 plus 3 minus 4. 1 plus 4, 5, over. And then, let's see. 1 plus 3 is 4. 4 minus 4 is 0. Okay. All right. This is another good problem. I'll be honest, I was expecting this one to come out differently, but I'm actually glad it didn't. Because this is another case. This is another case. Notice, in the previous problem, we had 0 over 0. That was indeterminate. This is non-zero on top and 0 on the bottom. So, this is not indeterminate. Okay, this is going to be either plus or minus infinity, okay? And I'm going to show you why, okay? But after I show you, it's important to realize that if you get a non-zero on top and a 0 on the bottom, immediately it's going to be one of these two, okay? We have to figure out which one's which, okay? So, let me point out one other thing. Since we have a 0 in the bottom, let's put this content together now. We have a 0 on the bottom, and division by 0, of course, is undefined. Okay? So, undefined. And, of course, that means we have a discontinuity. And because it's not 0 over 0, this is going to be a non-removable discontinuity. And in fact, it's going to be an infinite discontinuity. As you may have guessed from when we said the function went to plus or minus infinity. So good. So we're going to have infinite discontinuity. Now let's discuss that in detail. Since we're discontinuous, that means that the left-hand limit and right-hand limit are probably not going to be the same. So we need to examine the left and right-hand limit. Okay? So discontinuity, here's the line of reasoning. Line of reasoning is so important. Discontinuity, that means left-hand limit may not be the same as the right-hand limit. So we need to see if that's the case. So, left-hand limit first. And what I want to do, just to make this a little bit easier, is I am going to factor. So I'm going to factor the top. I want to pull out a greatest common factor of x. And then I'm going to factor the bottom. -4 and -3. That'll be x minus 4, x plus 1. And there we go. Look at that. X minus 4 goes away. And we're left with x over x plus 1. Now, again, this function, x over x plus 1, is going to be identical to this one, except at x equal 4. Okay, so identical except at x equal 4. Okay, and specifically, we have a removable discontinuity. Removable discontinuity at x equal 4. And it's removable because we can cancel, and then we can plug in 4 here to figure out what the value of that hole in this function, figure out where that hole is, in other words. Okay, so anyway, let's get back to the point, which was this, the infinite discontinuity at x equal -1. Okay, so let's do the left-hand limit. Let's do limit as x approaches -1 from the left. And we can use the canceled function because they're identical everywhere except x equal 4. And so we're talking about -1, no big deal. Now what I want to do is I want to I'm going to pick a number very, very close to -1, but to the left of it. So to the left means this, right? Think about our number line. Zero's in the middle. Positives are over here. Here's -1. I want to go immediately to the left of -1, which is somewhere here. Something like -1.0001. Okay? If I calculate that, if I calculate f of -1.001, where f is x over x plus 1, I'm going to get -1.001 over -1.001 plus 1, which is -1.001 over, and then this will still be -0.001, and of course negative over negative will be a positive, and we're essentially going to get positive 1.001 over 0.001. And this just means you need to move the decimal place over 3 times. So 1, 2, 3. This is like 1001. And now you can imagine what would happen if we took if we picked an x value closer to -1, like -1.00001, for example, then this would be much smaller, which means when I divide, I'll get something much bigger because I'll have to move the decimal place more to the right. Okay? So, in other words, what's happening, the left-hand limit here, the left-hand limit is positive infinity. Okay? This left-hand limit is positive infinity. And we've justified it here. Okay? Now, the right-hand limit, right? Let's pick a number very close to -1, but to the right. So, something here, something like -0.999, for example. Okay, so if I calculate f of -0.999, again, I'm plugging it into x over x plus 1. I get -0.999 over -0.999 plus 1, and that's -0.999 over, and then positive 0.001. And you do that division, you get -999. So the right hand limit then, look at that, I'm out of space. The limit as x approaches -1 from the right of our function is negative infinity. Okay. And so what does that tell us about the following, right? The original problem was this one. And then our function was, x cubed minus, x squared minus 4x over x squared minus 3x minus 4. We've shown that the left and right hand limits are not the same. So this limit does not exist, right? Positive infinity to the left, negative infinity to the right does not exist. Okay? So there's those. I think I'll call this video and start another.